Okay, talking about potential energy, but also known as energy of configuration. That you can think of several examples of potential energy you have encountered. Gravitational potential energy you've dealt with quite a bit. But it is energy of configuration. It has to do with the relative position of the penguin relative to the Earth. And if you make the two be further apart, then that new configuration has more gravitational potential. Or if you were to put the penguin on the spring, which I do not seem to be able to do, that the relative distance, we don't need the penguin, just the spring, that the relative location of the two ends of the spring is important to how much elastic energy there is. If you stretch the spring out, then there is more elastic potential energy because of this new configuration between the ends. Want to talk about the amount of work that is done, and the fact that if the work that is done in going between two locations, changing configuration, does not depend upon the path that you take between those two, then we say that the forces involved are conservative. Or alternatively, if getting from one place to another is the negative of the amount of work that is involved in going back, then we say that the forces involved are conservative. So if I put the penguin here and then slide him along this path, that work would be being done. I end up here in this new configuration relative to the center of the Earth, that I have had a loss of gravitational potential, and that is connected to the amount of work that was done. But if I were to then move the penguin back along that same path, when I get back here, I would do the negative of the work that I did getting there, and the penguin would have returned to the same potential energy he had before. So going over is the negative of the work in coming back, or alternatively, if it is path independent. So if instead I went between these two configurations by this route, I went straight over and then straight down, it should be the same amount of work as if I do it following this path. If I put the penguin on the spring, I still can't put him on the spring. But if we were to, if the penguin were to make the spring go down, then there would be a loss of gravitational potential energy for the penguin and a gain in elastic energy of the spring. But if the spring then pushed the penguin back up again, there would be a gain in gravitational potential and a loss in elastic potential for the spring, and those two ought to balance out. In the first case, positive work was being done on the spring as it became more energetic, and in the second case, exactly the same amount of work, but negative was done as the penguin returned. An important idea: conservative forces, specifically what's being conserved is mechanical energy. Well, I wonder if you could think of a case where mechanical energy is not conserved, and the force that would be involved, a case where the path you take matters. And the example that ought to spring immediately to mind is friction. If this path here were having friction, then as the penguin slid along it, negative work would be done. That is, the force from the friction would be opposing to the motion, but the displacement would be in the opposite direction, so that would be negative work that is done by friction, which in fact means that energy is leaving the form of potential and becoming heat. It's leaving mechanical and becoming heat. And when you get here, if you look at the potential energy and the work that is done, that more work was done than the difference in potential would be. And if you were to bring the penguin back, again, this time friction would not do positive work. This time again friction would do negative work, and so you would end up with a system that was significantly less in its potential energy when you made it back to the same configuration. That this would not be a conservation. And of course, if we went this way and avoided the friction, it would be much less work than if you went along the path with the friction. And it occurs to me that I failed to, on this page, talk about the fact that you have energy of configuration, and could you think of other forms of energy? And the answer hopefully would be kinetic energy, which is not energy of configuration or relative position, but energy of relative motion, and also heat, which is that form of energy that friction was just creating, and would not be energy of configuration. If you are just dealing with potential energy, energy of configuration, and kinetic energy, those are both mechanical energies, and we would find that the mechanical energy is conserved. Only when some of the mechanical energy becomes some other form, like heat, or chemical, or electrical, do we cease to have mechanical energy anymore, and we don't have conservation of mechanical energy. You don't have conservative forces. Here is a checkpoint where you can apply those ideas. You have these two configurations, A and B. You move between them. If you move this way from B to A, 60 joules of work is done. If you move this way, you're going against the arrow. That would be negative 60 joules of work, and so on. Are these conservative forces in this case? So, in the case where the only energies you have are mechanical energies, then the total energy of the system is not going to change. There's going to be no change in the mechanical energy, which means any gains in the kinetic energy would be at the cost of losses in the potential energy. You think about a penguin which is being dropped, and it's having a negative change in its gravitational potential energy and a positive change in its kinetic energy as it goes faster and faster, and vice versa. That the work, we recall, is equal to the change in kinetic energy, and so it would follow in that situation where energy is being conserved that the change in potential energy should be equal to negative work. That work plus negative work adds up to zero. That is a very hard point for people to remember. That work, of course, is the integral of force dot dx, but the change in potential energy, we need to remember to put that negative in there. That we lazily sometimes just put a U there because we assume that the initial potential energy was zero. But we need to be aware of that choice of zero that we are making when we do such a problem, that you can get into trouble with blithely assuming that the potential energy now, or the final potential energy, is the same as the change in potential energy. But in any case, don't forget that negative. Let's consider this penguin, with a little red dot on him. Let's consider this penguin and the work involved in lifting the penguin up. So the penguin is going to displace upwards, and you might mistakenly talk about the force of the penguin. That is the weight of the penguin that you are lifting, and say that the force times the displacement is going to be mgh, and that I am doing positive work when I lift the penguin. Therefore, the change in potential energy should be negative. Right? The negative of the work that I do, and my work I do is mgh, so the change in potential ought to be negative mgh. But that's not right. And the mistake is that we should not talk about the work that we are doing. Let me drag these guys off here. We're not talking about the work we are doing, but instead the work that the gravitational field, the Earth penguin system, is doing. And as the penguin goes upwards, the force acting on it, that mg, is directed downwards. So in fact, negative work is done when the penguin goes up. Negative work is done by the Earth penguin system. And then when you take the negative of that negative work, you see there is a positive change in the gravitational potential when the penguin is lifted to a higher point. That is very complex, and I always mess it up. In fact, I've had to record this lecture several times because I mess it up. But do your best to keep up with that idea. Here is the idea again, this laziness of saying that the potential is equal to mgh, where we gravitational potential, where we assume that this is an absolute value. But that is a mistake. It is the change in potential that is equal to the work that is done. That is mg times the change in your vertical position. That this sloth is like 4 meters above the ground, but he's 2 meters above this balcony. He's 0 meters above himself and 2 meters below the top of the tree. Well, those are 4 different heights, and if you put those 4 different heights in for h, you get a different value for how much potential energy the sloth has. But if the sloth is moved from that branch up to the top of the tree, that is 2 meters higher, then the change in potential was a gain of 2 times mg amount of joules. So this one is absolute. This one depends upon your choice of a 0, and you ought to be very conscious of that. Don't be lazy. Okay, here's a checkpoint, and the focus of this checkpoint is this change in potential energy. So we're asking to rank these according to the change in potential energy. This is a force versus position graph. So think about what work means in a force versus position graph and the relationship between work and the change in potential energy. And do that checkpoint. Another checkpoint where we have a change in potential energy, that this thing starts with a configuration of being up high, and it ends up with down at this new configuration lower down. So you have a change in the gravitational potential, and the question is, in which case would the kinetic energy be the greatest here when it gets to point B? And you rank them according to the one with the greatest kinetic energy to the one with the least. Think about what you're doing. And that concludes the show. Thank you.